So, welcome student. Let us start our lectures. Um, so this is course number MA412 linear algebra, and this lecture number 14. Okay. Now recall in our last lecture we defined a diagonalization of a linear operator. Okay. And then we proved some sufficient conditions. There are many ways, there are many necessary sufficient conditions are there, so we will prove one by one. So today we will discuss two important idea. So before that we need to start with something called some basic definition. So let us define this one by one. So suppose we have a vector space V over a field F, okay, and then we start with a polynomial. Say f belongs to, say, fx. Okay, this is some polynomial. So we say this polynomial, we say this fx. So this is fx. So you can think also this is polynomial over x. So the fx is nothing but you can write down p of f, right? The polynomials over okay. So you can write down this polynomial over f. Okay. So fx is or fx not is fx splits. Fx split over if you can write f in terms of you can write down fx is some constant time x minus some say a1 x minus a2 so I'm assuming that okay, so I did not assume anything. I'm assuming just a degree of f is something, say n, then x minus an, okay, where degree of f is equal to n. So degree means that the highest monomial whose coefficient is non-zero is called the degree, okay, and the coefficient of this highest monomial is called the leading term. So if you can write down fx in terms of this kind of linear factors, linear means degree one polynomial factor with some constant maybe, okay, then we say that this polynomial f is actually split over the field, okay. For example, there are polynomial which split over, like for example x square plus 1 does not split over R, but it does split over complex number, set of field of complex number, right? So this is over C. This is possible, but over R not possible. Okay. So with the help of these things, so we can talk about the relation between a diagonalization operator and the characteristic polynomial. Okay. So theorem. So if you choose that so given a operator if it is diagonalizable, then the characteristic polynomial must split. Okay. So what how do I write? So the characteristic polynomial, the characteristics polynomial of a diagonalizable operator always splits. over over the field, the same field. Okay. And so you can start with the definition. So the proof is also not difficult. So let me give a proof. So let T be a diagonalization operator. So T be a diagonalizable operator on V. Okay, then what happened? Then there exists a basis for with respect to that the matrix representation will be diagonal matrix, right? So you can write down that then there exists a basis a B, and you can write down also basis element in terms of B1 B2 something. So write down B1 B2 Bn of this is basis of V such that what happened? Such that the matrix representation will be diagonal matrix, right? With respect to this basis, some diagonal matrix D. So maybe we can write down. So you can write down that the diagonal entities are only constant, something C1, C2, Cn, rest are 0. These are all 0, right? So now what happened? If this is the matrix of that, then we know that how to find out the characteristic polynomial. Then the characteristic polynomial, then the characteristics is polynomial characteristic polynomial of T is given by how it will look like. So let me write down that is f of x. This has to be determinant of xi minus that matrix D, right? And because we showed that it doesn't depend on the basis, so whatever matrix with respect to one basis, if we change the basis, then the polynomial will be same, right? So what will be the determinant of this? So determinant will be x minus xi and then c, so c1, and then d, so everything is 0 here, 0 0 0, similarly 0, and the second matrix will be x minus c2, and then 0 0 0, and last entry will be x minus cn, right? Everything is 0 here, and hence the determinant will be what? Determinant will be nothing but x minus c1, x minus c2, and so on, and x minus cn. So that means that this characteristic polynomial actually splits, right? So it is product of these linear factors. So this is the proof. So that tells you that whenever you have a diagonalized operator, the characteristic polynomial must be a splitting polynomial. So it splits. But what of the converse? The converse is not true. You can find out a counter example. Okay. Similarly, in last lecture we learned that whenever you have a linear operator whose eigenvalues are distinct, then it must be diagonalizable, right? So to check something diagonal or not, if the eigenvalues are distinct, you can say diagonalizable. But if it is diagonalizable, you cannot say the eigenvalue are distinct. The converse is not true also there. Okay. Now with the help of all those things, so now we will define two definition, and these are going to help us. Okay, so definition. So we just learned that the characteristic polynomial split, right? But we never said that C1, C2, these are all distinct, right? It can maybe same also, right? So we can write down. So let the so 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 I don't know whether like this is diagonal or not. So let me write down that okay. So how do I write down? Okay. Okay, so let the characteristics polynomial. So okay, maybe I will write down the other way. That will be easier to understand. Okay. So so you start with the eigenvalues. So let uh, T belongs to LV, and you have some C is a CB, an eigenvalue of T over the field F. Okay, then we define something called algebraic multiplicity. Okay, then the algebraic algebraic multiplicity of the C is the so you write down you write down C is eigenvalue means what? C is a root of the characteristic polynomial, right? So when x minus c always divides the linear polynomial, x minus c divides the characteristic polynomial, right? The question is that what is the highest power it divides, right? So there might be more than one repetition, right? So I just want to know that what is the total number of repetitions of c inside the total number of roots of characteristic polynomial, right? So what does that mean? So is the largest or highest largest I should write down largest integer k for which the x minus c or k divides this the characteristic polynomial of t. So I don't care of t. Care of t means characteristic polynomial of t. Okay, or care poly, whatever. Care poly, whatever. Yeah. Okay. So this is, if it is fx, then we want to know that you write down fx. Okay. In terms of real factors, and what is the largest power of x minus c that divides this, and there is some another polynomial, maybe gx. Okay, and this GCD of x minus c and gx are 1. GCD means that there is no common factors, so x minus c does not divide gx in this condition. That means that whatever the power of x minus c dividing fx, that is already there. Okay, so this k is called the algebraic multiplicity of this eigenvalue c. Okay, and then there will be one more definition. So this is called algebraic multiplicity, and there is one more definition that is called geometric multiplicity. So geometric multiplicity of this C. Okay, so what does that mean? So geometric multiplicity is what? So this by this we mean that so geometric multiplicity of C is the dimension of the null space of, or whatever you can say, eigenspace. Okay, of the eigenspace. Eigenspace EC. Eigenspace means the eigenspace corresponding to the eigenvalue C, or you can say that this is the null space of this operator T minus Ci. Okay, all are same. Okay, so this is a subspace of the vector space V, and you check that what is the dimension of this subspace. So I'm assuming that V is fine dimensional. With that assumption, you check that what is the dimension of this. That is called the geometric multiplicity of that eigenvalue C. Okay, maybe let's give some example. So maybe my T is of this form, say 1 1 0 0 2 0 0 0 3, something like that. So random I chose. Okay, so now I would like to know that what are the algebraic multiplicity, geometric multiplicity. Okay, now obviously yeah, so this is one way. This is you can say by this obviously, but you can say another way also. So you know that eigenspace means the null space of this, right? Dimension of null space is called nullity, right? So this is, you can also say the nullity of this. So nullity of this T minus Ci. So what is nullity? T minus Ci, right? So that means this is also, you can write down that if the dimension of V is n, so you can write down that this is dimension of V minus rank of this, right? The rank of the matrix is easy to find out, right? Rank is the total number of independent rows or the independent columns, right? So that is easy to find out. So you can write down also this, and this you already know, and this is easy to find out compared to nullity. So you find out what is the rank, and then you take the difference, that will be the geometric multiplicity. Okay, so for example, here you see that the rank of this matrix is so this is a non-singular matrix, right? So determinant of T is not equal to 0, right? So that means that rank is 3, right? Yeah, so rank is 3. So what does that mean? Rank is 3. Rank is 3 means that rank of T, I should say, and the dimension of V is 3 also. So this is mapped from R3 to R3, you can 3, right? So that and then 1 minute. Oh, sorry. So this is rank of T is equal to 3. I have to find out rank of that null space. Okay. So rank of T minus Ci. What are the I? That's first you need to find out, right? So what are the C's? So so you find out determinant of Xi minus T. That you need to find out first. So what are these? So X minus 1. So this is X minus 1. And then minus 1 and 0 is 0, 6 minus 2, and then 0, and then 0, 0, x minus 3, right? So what is that? So determinant is this is x minus 1, x minus 2, x minus 3. Yeah, so this is that characteristic polynomial of T, right? Now obviously you can see that this is simple, that this splits here. Okay, maybe let me just change it. This is by 1, then it is by 1, this is by 1. So this you can write down as x minus 1 whole square, x minus 3. So now, so why I changed? I just want to show that there might be repetitions, right? So here see one is repeating roots, right? So you can say that the algebraic multiplicity of 1 equal to 2, and algebraic multiplicity of that eigenvalue 3 equal to 1. Okay. And geometric multiplicity also you can find out. So for 1, what you need to do? So you need to find out that what is how t minus 1 of I look like, right? T minus ci. So c equal to 1 here. So t minus ci is how it look like. So t is 1 0 0. Okay, so 1 1 0 0 1 0 0 0 3. That was the matrix. And this minus I identity matrix 1 0 0 0 1 0 0 0 1. So this is how it look like. So this is 0 0 0, this minus this is 0 1 0, this minus this is 0 0 2, right? Now see that there are two linearly independent columns here, and one is 0, so that means the rank of this has to be 2. That is clear from here. Rank of t minus I equal to 2, and hence the geometric multiplicity, which is nothing but dimension of v3 minus 2, which is equal to 1. Okay, so that's a bit clear, right? Or did I make a mistake? 1 minute. Sorry. So this is, there is a mistake. 1 minus 1 0 0 1. This is, this should be 1, not this. 1 minute. So this minus this is 0, and 1 minus 0, so this is 1. 1 minus 1, this is 0. 0 0, okay. But anyway, then still this is two linearly independent. This is rank, so geometric multiplicity of this is equal to 1, and geometric multiplicity is 1. Okay, and for 3, let us do it. So t minus 3i, so what is that? That is 1 1 0 0 1 0 0 0 3 minus 3 0 0 0 3 0 0 0 3. Now this matrix is, if you take negative, then what happens? 3 minus 2 0 0, 1 minus 0 is 1, minus 2 0 0 0 0. Okay, now here also there are two linearly independent columns or rows, so the rank of t minus 3i is also 2, and hence the geometric multiplicity of 3 is the dimension of which is 3 minus the rank of this 2 equal to 1. Okay, so now you see that for the case c equal to 1, that means that multiplicity for the case when the eigenvalue is 1, and the multiplicity and geometric multiplicity are different. But the case when the eigenvalue is 3, algebraic multiplicity and geometric multiplicity are same, right? So it may not be same always. Okay, this is an example which shows that it can have both the result can be same, it may not be same also, right? Now the question is that are there any relation between these two idea, right? So whether anything is they are related or not in general. Okay, the answer is yes, there is a relation. Okay, so theorem. So we have a linear operator T on a finite dimensional vector space V, and so V I am assuming that finite dimensional, maybe something say N. Okay, and I am assuming that C is an eigenvalue value of t. Okay, this is some assuming with say with algebraic multiplicity of c. So let me write down the song in this short form. AM is algebraic multiplicity. I mean to say that. Okay, that's c equal to say maybe m, and geometric multiplicity of c equal to say d. Okay, so let me write down this symbol d and m. So with that help, so this is true for any operator. Okay, it need not be diagonalizable. So in this case, then what happened? Then this d is always less than or equal to m. Obviously, d has to be at least one geometric multiplicity, but d is always less than or equal to m. So this can be equal to m. Sometimes, for example, in our last example, we see that when it's equal to 3, d and m are same. But when it's equal to 1, d is 1, m was 2, so they are not same, right? So in general, this is always true. Okay. So the proof is also not so difficult. So let us do the proof of this. The geometric multiplicity always less than or equal to the algebraic multiplicity of any eigenvalue. Okay, for any linear operator. So now, so let us the EC be the eigenspace, and eigenspace of C, okay, or corresponding to C, and your basis because I chose the dimension of EC is D, so you can have a basis V1, V2, Vd, BA, basis of EC, okay, over C, over F. Okay, now EC is a subspace of the V, so you can extend any linearly independent set to a basis of V, right? So extend this to a basis, say for example B, which is first the many vectors are the same vector V2 and Vd, and then you have Vd plus 1 to up to Vn, basis of V. Okay, so you extend this to basis of V, and then you want to know what is the metric representation of T with respect to this basis B. So so let me write down that. So let you have say A, which is the metric representation of T with respect to the basis B. Okay, then what happened? Then obviously these V1, V2, Vd are actually they are element of eigenspaces, right? So that means what? That means these vectors are also eigenvectors of T, right? So, and as V1, V2 up to Vd are eigenvectors of T corresponding to eigenvalue C corresponding to the eigenvalue C. What we have, so if you write down this matrix in terms of this basis V1, V2, Vn, and then the first D will be nothing but the diagonal matrix, right? Because the eigenvectors, so TV1 will be CV1, TV2 will be CV2, and dot C TV, right? So that is, so what happens? So T of Vi will be equal to CVi for I equal to 1 up to D. Okay, rest will be anything. Okay, so then then how this A will look like with respect to this basis? So A will be of the form, okay, so maybe something bigger. So first will be some C time identity matrix of order D, right? Because the TVI equal to CVI for I. So there will be a block D cross D block, which is a constant time identity matrix, C time identity matrix, and then obviously here will be 0 because rest will be 0, 0, 0, and there will be other two matrices, maybe something, some A1, A2, doesn't matter, some other block. So this is D cross D block, this is n minus D cross D block, and it can be anything, but this is 0. Now as this is 0, so you can easily find out the determinant. So what will be the determinant of this? So thus the characteristic polynomial, the characteristic polynomial of say t is f of x, that will be what? That will be first diminy. So this is determinant of your x minus I minus a, right? So the first diminy blocks will be x minus a I, right? So it will be having so x minus, so inside a you will have a kind of sum matrix of D cross D of matrix, which is a kind of diagonal matrix. In fact, this is identity times c, right? So that will comes out, and then you will have x minus c to the power d will be obviously there, and times something else. So what is the something else? So something else, so let me write down, this is the determinant of this. So this is determinant of this x minus c with this identity, because the identity, and then there will be something here, something 0 here, and then or maybe minus b, it doesn't matter because 0 is there, so it will get cancelled. And what will be the other term? Other term will be the matrix A2 is there, so it will be something c times identity matrix of the form n minus d. So this is n cross n matrix here, d block is there, so this will be n minus d block minus that A2, right? Now, so determinant will be this into this, so this portion will get out, and this will be something, some determinant of some another block c times n minus d of A2, right? Now doesn't matter, so it may be anything. And now note that c minus d, x minus c power d is already dividing the characteristic polynomial, right? But there is one more factor. So in that factor also you may have a factor of x minus c, but that doesn't matter to me. We know that at least there are d many factors which divides f of x, right? So what does that mean? That means the geometry multiplicity d is at least the algebraic multiplicity, right? The algebraic multiplicity may be more than that. So this implies actually d is less than or equal to m. Okay. So this is the proof. This proof tells you that geometry multiplicity of any eigenvector is always less than or equal to the algebraic multiplicity of geometry multiplicity of any eigenvalues is less than or equal to the algebraic multiplicity of the eigenvalue. Okay, so this much we understood. Maybe we will now try to prove some more important theorem. Okay. So now we will discuss the relationship between this notion of multiplicities with the idea of diagonalization of a linear operator. Okay, so how they are linked. Now for that I need some other results. So let me start with some proposition. So suppose obviously I am assuming everything fine dimensional. So dimensional is something finite, something n, and it is a linear operator on V, and we just for example we know that the characteristic polynomial of t which is split, right, if it diagonalizable, right, that we know, but in general we don't know they split or not, right? So we know only that there are so there are eigenvalues, for example maybe okay, so maybe x minus c1 power something, say m1, x minus c2 power m2, something like that, x minus ck power mk. This is characteristic polynomial of t. So this is polynomial polynomial of T. Okay. So so this C1, C2, Ck's are the distinct eigenvalues, and there are repetitions like M1 times C1 repeating. That means M1 is the algebraic multiplicity of C1. Similarly, Mk is the algebraic multiplicity of Ck. Okay, and this is, so let us assume these things, and now let also Vi are the vectors inside the eigenspace of this eigenvalue Ci, ECI. So Vi is a Vi are the things. What does that mean? That means TVI are nothing but Ci Vi. Okay, so this implies this, because Vi are the inside the eigenspace of Ci. So this is a null space of T minus Ci. Okay. Okay, so if this is happens, and so if with the help of all those things, if say V1, V2, dot Vk, there are k many distinct eigenvectors at the eigenvalues are there, C1, C2, Ck. If this is 0, this implies Vi equal to 0 for all I equal to 1 to k. So for all such I, this has to be 0. There is no other options. Okay. For example, it cannot be the case that you have some of those things are non-zero, some of 0. So we'll show that if this is the case, then you must have some contradiction. Okay. And the contradiction coming from the fact that eigenvectors corresponding to decaying eigenvalues are actually linearly independent. We know these things. Okay. So how do we do the proof? So proof of this theorem. Okay, so let us assume that there are first many things are non-zero. So on the contrary, suppose all Vi's are not 0. Okay. Suppose they are not 0, all Vi's are not 0. So there are some Vi's are 0, some Vi's are obviously you can assume that some Vi's are non-zero. Okay. Now what we can do, those Vi's are non-zero, we can actually renumber it, and we can keep it like first. For example, with the loss of generality, we can assume that first few many's are non-zero and later are the 0. So that we can do because we can renumber it. Okay, we can renumber the whole process, and that will gives you that first m of those are non-zero and rest are 0. Okay, so what is this? So we can assume that that V1, V2, this first m of Pm, this is 0, and rest like Vm plus 1 to Vk, these are 0. Okay. Now if these are non-zero, then what happens? If first m of those one is non-zero, that tells you that this vector V1, V2, Vm's are linearly independent. So this implies that this V1, V2, that set is linearly dependent over F. But this is a contradiction, because note that each Vi's are eigenvectors corresponding to distinct eigenvalues, right? But they must be linearly independent, right? So this is a contradiction. That implies that Vi has to be 0 for all I equal to 1 to up to k. So what does that mean? That means if you choose each vectors from eigenspace of different eigenspace, then their combination can be 0 only if each of those is 0. Okay, there is no other option. Okay, sum of those has to be 0. Now this is so this will help us to prove another proposition. So maybe proposition number 2, that tells you that if you choose a linearly independent set for each of eigenspace and take the union will be also the linearly independent set inside the full vector space. Okay, so again with the same setup, So with the same setup means you have C1, C2 and Ck's are distinct eigen values of T is a linear operator of V, and you choose some linear independent set. So let SI a subset of ECI be a linearly independent set. Okay. Then if you choose the union, then the union is equal to S1 union S2 union dot SK. So this is also a linearly independent set inside the whole V. Okay. So is also a linearly independent set in V. Yeah, and this proposition is very important because this will gives you the idea of relationship between diagonality and this multiplicities, right? Now the proof is actually coming from proposition 1, the previous proposition. And how do you prove it? So for to prove something is linearly independent, what do you need to do? We need to write down some trivial combination and show that the coefficient must be 0, right? So let me write down that. Let this set SI look like something like that. Say VI1, VI2 and dot dot dot. So something say VI of NI maybe. Okay. So like S1 equal to V11, 12, like the 1, N1, similarly S2 equal to 2, right? Like this. And then S will be what? So the S will be the union of SI, I equal to 1 to K, and that will be, you can write down that a kind of Vij, and your I is running from 1 to K, so 1 up to K, and your J is what? J is running from 1 to up to Ni, right? So maybe 1 to up to Ni. Whatever I you are getting with respect to that I, you can say, suppose I equal to 2, so it will go to n2 till n2. N2 is some integer. Okay. Now with that help we can take that to prove this set is linear independent. What do you need to do? We need to find out the constant, say Cij, such that Cij Vij equal to 0, and this is a double sum because there are so this Vi's Ij's are double sum, right? So your I is varying from 1 to K, and your J is varying from 1 to Ni. So J is from 1 to Ni. I is from 1 to K. Okay. So what happened with the help of this idea? You can ask with the help of this. You can. So let me just rewrite this in different way. So these factors, these Vij's are element of Vij, Cij. Now you are summing over J. So when you sum over J or Cij, so these are element of E lambda I, right? Because Vij's are okay. So let me write down. So this is a function of I, right? So let Wi is nothing but summation Cij is some constant time Vij, and J is summing over 1 to Ni, right? Now J is summing over 1 to Ni means what? So you are summing inside the set SI. So kind of when Wi equal to 1, W1 is nothing but V1 1 see this constant time V1 1 plus constant time V1 2 like that. So you are summing over this. So because these elements are these are inside Ci, so and Ci is a subspace, right? So the sum will be again inside Ci, right? So these are all element of ECI. Okay. So you can have element of ECI for each I, and that will gives you summation Wi equal to 0, I equal to 1 to K, right? But now from previous proposition, if we have vectors from each of eigenspace, if sum is 0, that implies the individual wi has to be 0. This implies wi is 0 is for all I equal to 1 to k, right? Now once you get all the ws are 0, that means what? That means that so this implies that summation so wi's are summation cij vi j equal to 1 to ni. This is 0, but these vij's are also element of si's, right? For each of I, this is element of si, but si is a linear motion, right? This implies cij equal to 0 as si are linearly independent set, right? And each vij is an element of si. So that implies that finally S is linearly independent inside V over F. Okay. So what does that mean? That means that if you have eigenspaces, if you choose some linearly independent set inside each eigenspaces and take the union of those in linearly independent set, then it will be a linearly independent set again. Okay. Okay. So this is a proof, and then finally, with the help of this, we will prove that that it is okay. So this is for finite rational vector space, obviously. So the polynomial split, and not only that. Okay, so let me write down that maybe properly, then you will have. So let T be a linear operator on V, and V is finite dimensional, so maybe dimension of V equal to n, and such that I'm showing that T split that means characteristic polynomial. So I should say such that characteristic polynomial of T split. Okay, that split over the field F. Okay, and so the split does not mean that it has all distinct eigenvalues. Eigenvalues may be repeated, right? So let me write down that say let C1, C2, and Ck are or be distinct eigenvalues. Eigenvalues of T. Okay. So then what happens? So then there are too many things happen. So number one, that then you can say that T is diagonalizable. If and only if this algebraic multiplicity is same as geometric multiplicity. So how do I write? So you already know that algebraic multiplicity, geometric multiplicity is always less than equal, right? So let me write down say GM of these CI's equal to AM of CI's is for all I. That means for every eigenvalues, the geometric multiplicity has to be equal to algebraic multiplicity. This is for every I. Okay, this is one thing, and not only that. So if you have if you choose the order basis for each of the eigenspaces and take the union, that will be the order basis for the next the full vector space. Okay, number two. Okay, so let me first prove this one, then we will go to number two. So proof. So there are two ways. Okay, so you need to first suppose. Okay, so let me write down that my DI's are actually geometric multiplicity of CI. So that means this is the dimension of ECI's, and MI's are algebraic multiplicity of CI's. That means the highest power of x minus CI, which divides the characteristic polynomial. Okay. So with the help of these, so there are two ways, right? So suppose that T is diagonalizable first. Okay, so if T is diagonalizable, then I need to find out that algebraic multiplicity and geometric multiplicity are same, right? Now, when you have a diagonalizable matrix, then what happens? Then you have a basis. That basis actually consists of all the eigenvectors of T. Okay, so let B. So let me write down B a basis containing all eigenvectors of T. Okay, so this is the meaning of diagonal algebra. Okay, now if you have eigenvectors, then you can do one thing. You can check that how many eigenvectors are actually belongs to which eigenspace. So let me write down these symbols. Bi's are B intersection ECI. So ECI is an eigenspace corresponding to eigenvalue CI, and into intersection, and that will be BI. Now, so these are the kind of those eigenvectors which are element of the eigenspace also. Okay. So now suppose you write down that how many. So you just want to know that what is the cardinality of BI. So let me write down that maybe Ni is the cardinality of BI. Okay. Then if Ni is the cardinality of BI, then what happens? So what is the relationship between Ni and BI? So what is BI? So first of all, BI has to be linearly. So whole set is linearly independent, right? So BI's are also linearly independent, and you know that dimension. So each BI has linearly independent vectors, and dimension of BI's are, so BI's are inside ECI, right? Dimension of ECI's are DI's. So number of linearly independent vectors inside a DI dimension vector space cannot be more than DI, right? So this implies actually the Ni has to be less than equal to DI as this dimension of ECI's are DI's. Okay. So, and BI's are a subset. It consists of linearly independent vectors. So that has to be less than equal to DI. So this is one way. And also you know that these DI are actually less than equal to MI, that we already proved in the first step. So we already proved that this algebraic multiplicity is bigger than equal to multiplicity, right? So this has to be this. So with the help of this, what you can say that now there are two ways. Now you will sum it. How do you sum it? You will sum all those Ni's I equal to 1 to k, and you know that Ni's are cardinality of Bi's, so sum will be cardinality of B, which is N. On the other hand, Ni less than equal to Di, so it will be sum over Di's I equal to 1 to k, but Di's are also less than equal to Mi, so this will be less than equal to sum of Mi I equal to 1 to k, right? But Mi's are the algebraic multiplicity, right? And if you take sum of those things, so it will be the total number of roots that has to be equal to n, because the characteristic polynomial has degree n, right? And I know that this diagonal I assume the diagonal, that means that split, right? So once in both sides you have Mi and left hand side n, also right hand side d. What does that mean? That means if you take the difference of Mi and minus d, that's 0. So this implies that this summation, this Mi minus di, or rather di minus Mi, whatever you choose, the difference is actually 0, right? Because it is upper bounded by n, lower bounded by n, and this implies that di has to be equal to Mi, and that is true for all I equal to 1 to up to k. So what does that mean? That means when something is diagonalizable, they choose a basis consisting of eigenvector and then take the restriction in the eigenspaces. You will have corresponding eigenvectors inside the eigenspaces, right? Now you count how many linear independent eigenvectors are there, and then use that already known fact that geometric multiplicity is less than equal to the algebraic multiplicity. And with the help of that, we just prove that this has to be 0, right? This has to be, so it cannot be negative, right? So, or other, okay, so yeah, so if you have problem, you can write down the other way also, summation like this way also, summation mi minus di. Now mi is always greater than equal to di. This has to be either 0 or positive, so you can say like that also. So then that means each of those factors are 0, so mi equal to di. Okay, so we just prove one side that diagonalizable means that algebraic multiplicity and geometric multiplicity are same. Now conversely also we can prove conversely, suppose that mi equal to di, then if mi equal to di, then what happens? Suppose I let mi equal to di for all I equal to 1, 2 and k. Now if they are all same, then what you can show, for each of I you find that you choose that basis of each. So let me write down that suppose bi be a basis of that ECI, right? The eigenspace corresponding to the eigenvalue Ci. Now, if this is basis of this, means this is also linear independent, and then we just prove in previous proposition that union of this bi I equal to 1 to k, and this is also a linearly independent set inside V, right? Because each of bi's are linearly independent inside ECI. So the whole thing is linearly independent. Now, question is that then is this a basis? The answer is yes, because the cardinality of this is what? This is actually this is nothing but cardinality of di's I equal to 1 to n, so 1 to k, because each of bi has a cardinality di, right? But di equal to mi, so that will gives you that this is summation mi I equal to 1 to n, summation mi, sorry, 1 to k, summation mi equal to also n. So the number of vector inside this linear independent set V has n, which is exactly equal to the dimension of V. That implies that this is also a spanning set, and di is a basis of V. Okay, so what does that mean? That means if you start with mi equal to di, then each basis of eigenspace, if you take the union, that becomes the basis of the whole space, right? And eigenspaces are what? Eigenspaces are those bases of eigenspaces are nothing but the eigenvector, right? And hence BB is actually a basis consisting of eigenvectors. Also B contains all eigenvectors of T So what does that mean? That means T is diagonal. Thus T is diagonal, right? Diagonal. Okay. Okay, so this completes the proof. So this also proves that if T is diagonalizable, then each basis of eigenspace, the union will be the basis of the whole space. Okay, so this completes the proof. So I will stop here.